chapters of Chennai as well as Kalpakkam, and Chennai chapter doing it for this year at IIT Madras. So to begin the program, let me call upon the stage Professor Pratap Haridas, the Dean of Academic Courses, who will be presenting the Chief Guest address. Then I would like to invite the Chairman of the Placid Rodriguez Memorial Committee, Professor Kamaraj, to please come on the dais. Then I would like to call upon our special invited speaker, Dr. Debashish Bhattacharjee, to please come on the stage. And the Indian Institute of Metals Chennai Chapter Chairman, Dr. Murugayan, to please come on the stage. So we'll begin the program with the welcome address to be provided by Dr. Murugayan Amadalingam, who will be presenting about a brief welcome to all of you and as well as about the lecture itself. Yeah, Dr. Murugayan.
Good afternoon, colleagues, students, Madam Blossom Rodriguez, Dean Pratap, Dr. Bhattacharjee, Professor Kamaraj, and colleagues from Kalpakkam. So it gives me a great pleasure to invite all of you for this year's Dr. Placid Rodriguez Memorial Lecture. And this lecture is actually jointly organized between Kalpakkam and Chennai chapters of Indian Institute of Metals. So this year we have Dr. Debashish Bhattacharjee to deliver a talk on opportunities in new materials in India. So I welcome on behalf of both IIM Kalpakkam and Chennai chapters Dr. Bhattacharjee to this event. And I also extend my hearty welcomes to all the viewers who are watching this in YouTube Live as well. And thank you again and welcome all of you to this year's event. Thank you.
Thank you, Dr. Murugayan. So now I may call upon Professor Kamaraj to present about the Dr. Placid Rodriguez Memorial Lecture Series and the details associated with it. Professor Kamaraj.
So, good evening to everyone. Once again, I join with IIM members of Kalpakkam and Chennai chapter. I welcome you all this 14th Dr. Placid Memorial Lecture. To say a few words about the PRML of Dr. Placid Rodriguez Memorial Lecture, to perpetuate the strong scientific spirit and the value system which Dr. Placid Rodriguez practiced during his lifetime. Dr. Placid Rodriguez Memorial Lecture was instituted by the Indian Institute of Metal in 2009 under the pioneering leadership of late Dr. Baldev Raj, then Director of NIAS Bangalore and former President of IIM. Since then, the event is being organized annually by the Kalpakkam and Chennai chapters of the IIM. Dr. Placid Rodriguez, born in Koilan, Kerala on October 5th, 1940, obtained his BSc from Kerala University, BE Metallurgy from Indian Institute of Science, Bangalore, and MS from University of Tennessee, USA, and PhD from IIC, and MBA from Indira Gandhi National Open University. He joined the Department of Atomic Energy in 1960, then moved to the Indira Gandhi Center for Atomic Research, then known as the Reactor Research Center, in 1974. He established one of the leading metallurgical research laboratory at Kalpakkam. He was the director of IGCAR of Kalpakkam from 1992 to 2000. Subsequently, he served as the chairman, Recruitment and Assessment Center, DRDO Delhi, and Raja Ramanna Fellow, and AICT INIA Distinguished Visiting Professor at IIT Madras. Dr. Placid Rodriguez had exemplary career of 4 decades leading research in metallurgy, materials development for fast reactor program and our country in shaping up human resources in defense program and academic institutions. Dr. Placid Rodriguez has been a member of editorial board of several reputed international and national in metallurgy and material science, and he was the chief editor of Transaction of Indian Institute of Metals. Dr. Placid Rodriguez served as the president of many leading national professional institutes. Dr. Placid Rodriguez has been a recipient of many national international awards. He has been fellow of many prestigious academics of our country. Dr. Placid Rodriguez passes away in Chennai on 31st August 2008. So in memory of Dr. Placid Rodriguez, we used to organize every year on 5th of October, but this time we could not do it because of our Dasara festival. We could not do it on 5th October. And also I would like to mention that previous speakers of memorial lectures delivered about Rodriguez Memorial Lecture. The first lecture, as I mentioned to you, it was instituted 2009, which was delivered by Professor Atul Choksi, Indian Institute of Science, Bangalore, followed by Professor Siram Ramakrishna, National University of Singapore, 2010, and Dr. Srikanth, Director NML, Jamshedpur, 2011, and 2012, Professor B.S. Murthy, IIT Madras, Professor Indranil Minna, Director, IIT Kanpur, 2013, Dr. Amul Kogle, Director, DMRL, Hyderabad, 2014, and 2015, Dr. G.K. Day, Associate Director, Materials Group, BARC, Mumbai. Dr. A.K. Bahaduri, Director, IGCAR, Kalpakkam, delivered in 2016, and Dr. U. Kamachi Mudali, Chairman and Chief Executive, KV Water Board, Mumbai, in 2017, and Dr. Samir V. Kamath, Director General, Naval System, DRDO, 2018. Dr. S. Somnath, Director, VSSC, ISRO, Trivandrum, 2019, and Dr. Surya Kalandi, Georgia Institute of Technology, USA, which was held in 2020. And last year, Dr. B. Venkatraman, Director of IGCAR, Kalpakkam, delivered Dr. Placid Rodriguez Memorial Lecture. And this is going to be the 14th lecture. And once again, I welcome you all for this Dr. Placid Memorial Lecture. Thank you.
So thank you, Professor Kamraj, for sharing the brief note. So now let me invite Professor Pratap Haridas, the Dean of Academic Courses at IIT Madras, to present the Chief Guest Address.
Good evening, everyone. It's a privilege to be part of this event to show our respect to the various contributions of Dr. Placid Rodriguez. I think it's very fitting that we use this opportunity to meet as a larger community because I think traditionally with all the activities we all get involved in, we tend to get into silos. Academic people are in the academic world. The industry people are in their own world, and we don't really get an opportunity to meet in a relatively free setting where we don't have a specific agenda of giving a project or taking some specific consultancy or any such thing, but just to exchange information, to learn from each other, and so on. So I think it's very important in any aspect of engineering to build this sense of communities that we are in this together. Because it is true that the industrial sector is, if you ever worked in an industry, you will find their focus on a daily basis is very different from what, as a student or as a faculty, you may tend to see in an academic setting. And each has its value. So there is no specific reason to believe one is better than the other and so on. And I think opportunities like this help us see the other side of the world in much greater clarity. And I think over the years, we have seen really distinguished speakers participate as part of this lecture series. And today we continue the tradition. We have Dr. Debashish here, and I'm confident that we will all be quite enriched by listening to his talk as part of this event. Thank you all, and I hope we'll have a good evening. Thank you.
Thank you, Professor Pratap. So now I would like to invite Dr. V. Karthik, Vice Chairman of IIM Kalpakkam chapter, to introduce this year's PRML speaker.
Good evening, ladies and gentlemen. It's a great pleasure for me to introduce our speaker of the 14th Dr. Placid Rodriguez Memorial Lecture, who is going to talk to us the opportunities in new materials in India. This is a subject which we all would be deeply interested because it holds the key for the future of Atmanirbhar India. Today we are very fortunate to have Dr. Bhattacharjee, who is an expert in development of materials and associated technologies. Our speaker, Dr. Debashish Bhattacharjee, is currently the Vice President Technology and New Materials Business, TATA Steel, based in Kolkata. He joined TATA Steel in R&D function in 1996 after a prolific academic career that includes BE in metallurgical engineering from the Jadavpur University in 1986, MTech in metallurgy from IIT Kanpur in 1989, and PhD in material science and metallurgy from the University of Cambridge, UK in 1993. Serving as the Chief of Research and Development and Scientific Services in 2009, he was seconded to the Tata Steel Europe as Group Director Research, Development and Technology for Tata Steel Group. He is also responsible for setting up new businesses in materials beyond steel, like in composites, graphene, and medical materials. Dr. Bhattacharjee is a fellow of the Indian National Academy of Engineering and of the Indian Institute of Metals. He is a visiting professor at the Imperial College of London and at the University of Warwick, UK, and at the University of Science and Technology in Beijing, China. He has received the Metallurgist of the Year Award by the Government of India in 2004 and the IIM Tata Gold Medal Award in the year 2021. He holds about 20 patents and also recently edited a book titled Future Landscape of Structural Materials in India by Springer, which is a must-read book for every one of us. With these few words on a very inspiring profile of our speaker, may I now request Dr. Bhattacharjee to kindly deliver the 14th Placid Rodriguez Memorial Lecture.
Thank you. Can you hear me? Am I audible? Thank you. Thank you, Dr. Pradeep, for this rather humbling introduction. Thank you for the organizers for inviting me and giving me the. It's an absolute honor and privilege to be here speaking and delivering the Dr. Placid Rodriguez Memorial Lecture. So, Dr. Murugayan, Dr. Kamraj, Professor Haridas, Dr. Pradeep, all the faculty members here from IIT Madras, students and colleagues from IGCAR, other members of the IIM chapters. I'm really grateful that you have considered me to be the 14th speaker of Placid Rodriguez Memorial Lecture. And I'm more than ever honored that Mrs. Rodriguez herself is here, and my deep respect to the soul of Dr. Placid Rodriguez, and I pray for your well-being and continued good health going forward. I had met Professor Dr. Rodriguez way back in the 1990s and the 2000s in Jamshedpur, mostly in Jamshedpur when he used to visit on IIM affairs, also on NML affairs, and sometimes when Tata Steel invited him for giving special lectures for us to open the window to the world of materials, to the world of mechanical metallurgy in which he was an expert. And it just so happened that my PhD was also in that area of fracture and fatigue, though it seems a lifetime ago that I worked in fracture and fatigue, and now it's more about getting the top line and the bottom line going, not so much as crack growth. Yeah, but it's a curve anyway. It's a line that goes up, right? But again, I'm really grateful that you have invited me for this lecture. I will not be talking on academic affairs, but I will be talking on the influence of academia, influence of new science going into technology going into the market as new products, new materials, and giving our nation leadership position in the world, in at least in the area of materials. Professor Haridas mentioned about the industry and academia, like East and the West, the twain shall never meet. But I think these are the occasions when the twain do meet. And again, thank you for giving me this opportunity. And these are, you'll not find equations here. You will hardly find microstructures here. But I hope you will find the story interesting as to how things evolve, especially in the area of materials. So I have, as was told before, I have worked, in my PhD, I've worked on fracture of steel, of aluminum alloys, of even polymers, PMMA. In my first postdoc, I worked on nickel-based superalloys, thermomechanical fatigue, and in my second postdoc, I worked on mechanical deformation and prediction of toughness, which is very difficult. Prediction of strength is easy, but prediction of toughness is more difficult. But prediction of toughness in hot-rolled high-strength HSLA steels. But then I've moved on. I've worked on and in about steel from 1996 to 2017. And then I had the opportunity and the privilege of picking up materials beyond steel, so setting up businesses in non-steel materials. So you know, I'm sort of lucky to be in a position where I can talk on steel, and I can also talk on what we can or cannot do in non-steel materials. Right? So I'll give you a glimpse of what I have learned in these years, and hopefully this will result in further communication and dialogue between academia and industry. So material-wise, steel is not going to go away. The world makes about 1.8 billion tons of steel. That's 1,800 million tons of steel. Total value of that steel, roughly, rule of thumb, is about $1 trillion. That's $1,000 billion. It's used in almost every aspect of life, from safety pin to the aircraft carrier. Everywhere there is steel. The automotive is steel, the train is steel, the bridge is steel, the chair you're sitting on is made of steel tubes, so on and so forth. The nearest competitive material is aluminum. I'm not talking about concrete. Yeah, the concrete is more than steel, but I'm talking about metallic and non-metallic materials, not aggregates. Nearest competitive material is aluminum, and the world makes about, in terms of value, so $1 trillion is steel, aluminum is about $200 billion. So that's the gap, right? The nearest competitor coming up very fast is polymeric and polymeric-based structural materials, which are fiber-reinforced polymer composites. This could be glass fiber reinforced, this could be carbon fiber reinforced, this could be aramid, basalt, or even natural fiber reinforced. But 65% is glass fiber reinforced around the world, and that's about $100 billion. So you have $1 trillion steel, about $200 billion aluminum, and about $100 billion nearest competitors is FRP composites, fiber reinforced polymer composites. You talk about titanium, the world global market is about $15 billion, $20 billion. So that's the scale we are talking about. So none of these materials is actually going to be a threat to the volume and expanse and extent of steel. It's increasing, and it's going to increase as countries expand in their infrastructure. India is a country which is massively increasing in its infrastructure. India today produces the second highest number in terms of tonnage amount of steel in the world. China produces 600, 700 million tons. India produces and consumes about 110 million tons of steel, and it is number 2. But if you look at how much India can consume, given by global standard of a mature country consumes about 300 kilograms per person per year of steel, which for a 1.4 billion, 1.3 billion population, it comes out to about 350 million tons. So India eventually is going to go to 350 million tons. Whether it is going to be 2030, 2040, that's a matter of debate, question, and how future unfolds. But that's the amount of steel eventually, as a mature country, India would need continuously. Today, India is at 110. It's going to go to 300 eventually. It's going to pass through 200, 250. Those are large numbers. So whatever steel India produces today is going to double, is going to triple. But there will be areas in which other materials will compete. And you're seeing that competition come in today. You're seeing the car, for example, which used to be all steel. Large parts of a car, even the exterior, is not steel anymore. You don't make out. But they're not steel anymore. The bumper, which you think is very safety critical, is not steel. The bumper is plastic. And the technology today is so mature in that particular aspect that the color, the shine, and surface finish wise, you can't make out unless you touch and give it a knock. And you'll see the knock on the bonnet and the knock on the bumper. The sounds are different. The bonnet is clearly metallic, and the bumper you'll find for almost all cars is plastic. So unknown to us almost, this transition is already happening, where other materials are taking over traditionally used materials. And this is usually driven by mega trends. There are many trends that are happening in the world which define the way we behave, define the way industry behaves, and define the way the politicians bring in regulations. Right? And these are megatrends such as lightweighting. And the world needs lightweighting because weight means more energy consumption. And if you are consuming oil, you're also giving out more CO2. So the world is going to go towards lower weight, lightweighting, and that therefore it's going to always try to use lighter materials. And those of you who know steel, they know that the move of steel towards higher and higher strengths and higher ductility is driven by the fact that you need to use lighter weight steels in a car, right? But then eventually, when it comes to cost effectiveness, some other lighter material will come in and win the competition. Plastics and fiber reinforced composites are 1/3 the density of steel. At some point, they will win on the lightweighting game. And therefore, bumpers today are FRP or plastic. Environment and sustainability. It's a one-way street. The world, in spite of Germany suddenly liking coal because Russia has switched off the gas lines, is a temporary affair. The world will go towards low carbon energies. The world will go towards low CO2 emission. And that is a mega trend which will drive many, many behaviors and many, many transitions in the industry. And you're already seeing battery-powered vehicles, electric vehicles on the roads. And that, again, to use a not very nice simile, or maybe a much used simile, it's a one-way street for vehicles, which is to go towards electric vehicles. Of course, the electric vehicles need the batteries to be charged, and that battery is charged today by electricity which is generated by a coal-based power plant. So there is CO2 at some point in the power. But nevertheless, in 5, 10, 15 years' time, that power is also going to be green, and eventually you will have green electric vehicles on the road. That is the mega trend going forward. So industry, whether it is vehicles, whether it is manufacturing, whether it is airlines, is driven by consciousness about environment and sustainability. Those are mega trends. And health. There are many. I've just chosen three. As you know, in the 1940s, around Second World War, the average longevity in India, guess how much it was? How many years was the average longevity? 1940s was about 30 years. In UK, which was then ruling the world and the sun never set, was about 45 years. And of course, medicine transformed everything. Penicillin transformed everything. Availability of more advanced surgery techniques transformed things, and longevity went up. Today, India's average longevity is about 66, 67 years. In the West, it's close to 80 years. So people live longer. And as people live longer, there are other ailments that come in which need to be treated. So the amount of treatment needed for people to remain healthy is going up. People live longer, people need more treatment, and the other factor that has happened is people can also afford medical treatment. And of course, nobody will grudge an ailing person medical treatment, right? So health is a northward megatrend, which is health requirement will always go up. Demands for cars may go up and come down. Demand for airline travel may go up and come down, but demand for health will not come down. It will always go. It's like education. Right? So these are some of the mega trends. Only three I've written. There are more, which determine what material eventually will be used in which application, right? And which material will be needed by the population, by the country, for whatever strategic reasons. So this determines strategy. So given this, we as Tata Steel, we felt we needed to look at materials beyond steel. And I've just told you about how in a car which we think is all steel, other materials are already coming in. Just give you the example of the bumper. If you look at trucks, right? The trucks carry diesel and fuel tanks. Those fuel tanks are transforming into multi-layered polymers. So that's another business of steel gone. So this thing will keep on happening, and we decided that we, as a 115-year young company, reasonably good in one material, that is steel, we need to have our leadership position in other materials as well, as they make their footprints more visible in the future. So we need to maintain our leadership position in materials domain as such. So we decided to go into composites. Composites, of course, is a structural material. There's a group of structural materials. They go into sectors which steel goes into. So in many aspects, one part of Tata Steel's business is competing with another part of Tata Steel's business. So but then the competition is based on multiple factors. It's based on whether lightweightedness is important, or superior strength to weight ratio is important, whether chemical and corrosion resistance is important, and whether it's important to mold the material into complicated shapes very easily. And of course, the underlying factor is cost, right? And all that happening at the right cost. So worldwide, the growth rate of composites, given all these factors, is in double figures. In India, the worldwide market, as I've said, is about $100 billion. India is small. Like in any material, to start with, India remains small. Even today in steel, India is second in the world in volume. It is 100 million tons out of 1,800 million tons. Yeah, so it's fraction-wise, it is small. So not surprising that in these new materials, India is small as a percentage of the world. So out of the $100 billion of market in the world, composites market in India is roughly 1.5 to $2 billion. So 1%, 2% of the world. Forget these numbers, and it's projected to grow, of course, and the growth will come from some sectors I'm going to talk about later. But today, being small as a nation, imagine, I don't know, again, if you're aware of the steel industry used to be very fragmented, with a lot of small players, till consolidation happened and few players became very big. The same is with composites industry in India. The biggest is around, that's an outlier, they do many other things, is around less than 500 crores out of 15,000 crores. And there are a whole lot of companies around 100 crores, 50 crores, etc. They are very small companies. And what happens when you have a scenario like this with largely medium sector and small and medium sector is that they don't invest in R&D. And our ecosystem isn't conducive to large companies, academia and medium sector coming in to play, just like in, say, unlike in Germany, where Fraunhofer forms a platform where large, medium companies come in and academia is there as well. We don't have a structured way of doing that. So they are not technically very advanced. So while India is very small, it's also not technically very advanced today. But things will change. Right? Where do these composites go today? They go into poles, they go into pipes. We were as Tata Steel, we were the first to make bridges out of composite materials. So there are 3 bridges all in Jamshedpur, in the steel city, just to make a point, that's made out of glass fiber reinforced composite. They go into chemical tanks for the corrosion resistance. They go into street furniture. They look beautiful. They're easy to mold. And again, in bus stops and things like that. But as you can see, these are not, except for perhaps pipes and chemical tanks, these are not high volume business. This will not drive the nation's composite market from $1.52 billion to $20 billion or $50 billion. What will drive the nation's composite market is large sectors, automotive, railways. And Indian Railways is changing like nobody's business. I'm sure all of you travel by train, and you know, we are very accustomed to seeing the train inside, the carriages inside made of plywood or very rusty, hot-rolled steel, where you can actually see the scales behind the paint, very shabbily done paint. Indian Railways doesn't want that anymore. Indian Railways wants the passenger coaches to look like European passenger coaches, both from outside and inside. So we are working with Indian Railways to give composite material solutions for the entire inside of passenger coaches. So we are working on the entire cabin, the windows, the roof, the floor, and also the seatings. The first few you've heard of the Vande Bharat trains. The first couple have come out. The next 20 will have our seats in the Vande Bharat Express. The next 20 will have our interiors in the Vande Bharat Express. These are large sectors which will drive growth of composites in India. Right? And we are there. We are just setting up a plant in Khopoli in Pune, from where we will export composite materials for use in European railways at European standards. So we're bringing in technology that will upgrade the nature and the quality of composites that's available in India. moving to another material, which is a completely different material from composites, is graphene. And this audience would have heard of graphene. I don't need to describe what graphene is, right? Okay, it's a single layer or maybe multi-layers, 1, 2, 3, 4 layers of graphitic, atomic layers of graphitic carbon, right? Tata Steel in 2009-10 started working on nanomaterials for industrial applications, and that work led to work on graphene. 4 or 5 years back, we decided. So we have our own intellectual property in graphene, in the production of graphene, and we have our own intellectual property in application of graphene. Today, in terms of pure graphene production, Tata Steel is among the top 10 in the world. We have a 100 tons per annum graphene production plant in Jamshedpur, using 2 of our technologies, which I can talk about later in more detail if you want. And we are looking at application of these graphenes in polymers, in coatings, in energy storage, also in textile and composites. And I'll talk to you a little more about this. So we have about, this is the plant in Jamshedpur which has a capacity of 100 tons per annum, and it's called Graphite, which is a very obvious name. So today we use graphene, and we have about 50 patents around graphene and its applications. We use graphene in dispersions in paints, adhesives, and waterproofing. We use graphene in thermoplastics, and we have a range of thermoplastic pipes with a brand name of Wondra, whose properties are enhanced through graphene. The properties of the pressure that they can take, and very, very importantly, it increases strength level, and therefore when you recycle this, normally the strength level drops, but because it's increased strength level, it can take 3 to 4 recycling before its strength level drops below the acceptable limit. So graphene in thermoplastic pipes makes thermoplastic pipes recyclable. So that hits sustainability in a big, big way. It's a positive on thermoplastics. We use graphene in elastomers, rubbers, in conveyor belts, in retreading of tires, and life goes up by 2 times to 3 times. And of course, it's not just sprinkling of graphene in an elastomer or polymer that will work, for you to make the formulation to work. So there's a lot of research that goes on behind. Today, so there you are. We put graphene in structural coatings to reduce corrosion, and this is already applied in our plants that are close to the coast. We put it in adhesives, mainly for structural adhesives and also to join pipes. Graphene-enriched HDPE conveyance pipes, and you can see the retreaded tires and the liners. So this is a liner for a dumper truck. The dumper truck body is steel, and if you leave it as steel, it wears off very fast because there are rocks falling on it or iron ore. But if you put a rubber lining with graphene in it, the wear resistance goes up. And instead of changing the main steel body, after about a couple of years, you only need to change the rubber liner. But without graphene, the rubber liner doesn't last. But with graphene, it lasts. So maintenance time comes down, cost comes down, availability and productivity go up. So from Tata Steel today, we have a whole range of pipes. We have mild steel pipes, we have ductile iron pipes, we have graphene-enriched HDPE pipes, and we have fiber-reinforced polymer pipes going from few inches in diameter, all of these, to 2.5 meters in diameter. right, for all sorts of pressure conditions and pressure head conditions. And of course, recyclable. Before coming to medical materials today, we are one of the top 10 in volume capacity of graphene production. Our graphene business is 75 crores per month. At this, it is one of the top 2 in the world in graphene to make commercial use of graphene. And I think this puts India right at the top in the leading edge of graphene production and graphene usage. It's a material that otherwise around the world people find it very difficult to use. Right? And our graphene commercial usage numbers, 75 crores per month, is on an upward tick. It's doubling every 6 months. So looking at the mega trends, we addressed lightweight materials, composites, and we're looking at large evolving sectors such as railways. We're also looking at railway wagons, I forgot to mention. Wagons that carry salt and coal, they actually carry acid, hydrochloric acid or sulfuric acid, essentially. And they corrode very fast. So by specification, they should have, these wagons should be made of austenitic stainless steel. But that's expensive, not easily available, and not very easily maintainable, right? So we have given a solution of using FRP for these wagons. And at this very moment, we are working with RDSO, which is the Railways Design and Specification Organization, with the permission of the minister himself, working on 2 rakes, that's 120 wagons of FRP material as prototype for transporting salt and coal. Going by the megatrends, I mentioned health. And as a materials company that's interested in materials beyond steel, we could not ignore health. So we delved into medical materials. And of course, medical materials is a huge area. Roughly, you could consider medical materials and devices into 4 segments. Diagnostic imaging, so you have these X-rays and CT scanners and the materials involved in those. You have instruments and appliances, which are mostly stainless steel. You have patient aids and implants, which are again metallic as well as ceramic. And you have the consumables and others, which are again ceramics and also some textile. Right? There could also be bandages. There are protein supplements and things like that. You don't need to total it up. The Indian market, just the Indian market today is about 65,000 crores in medical materials and devices, not medicine. Nearly 75% of this is imported. What is not imported are the simpler materials, needles, bandages, and so on, so on and so forth. But even a basic material such as hydroxyapatite, which is calcium phosphate in a particular crystalline form and morphology, is imported. Nobody manufactures at the medical grade hydroxyapatite in India. And this hydroxyapatite is needed for coating on implants. An implant made of stainless steel or titanium coated with hydroxyapatite makes assimilation, bone assimilation easier, and therefore curing time less. So and so forth. Hydroxyapatite is used as bone fillers, right? It's used in dental, it's used in most orthopedic operations. But that material is entirely imported. So we decided to make a difference. We decided that we will not import even technology. That's the hydroxyapatite point. We decided to work with IISc Bangalore. Professor Bikramjit Basu, who is one of the leading biomaterials professors, and with Ramaya Medical College, with the Medical College in Kerala, and with a startup company which is proficient in advanced ceramics manufacturing. we are steel makers. We understand ceramics, but we're not advanced ceramics manufacturers. So we created a company called Ceramat, which is a Tata Steel company. The steel is run, the company is run by the advanced ceramics experts. And we are producing at commercial scale hydroxyapatite made using the technology from ISC Bangalore. Its quality is the best in the world. We have benchmarked it in India with imported products. We have sent our products to Belgium and US for benchmarking, and it matches perfectly. Of course, it's gone through a lot of pain and hardship in evolving not only the process, but also the equipment necessary to produce at that quality. But today we are ready to market, and it is being test marketed today as hydroxyapatite for coating on implants. So this is hydroxyapatite being produced in all glass vessels. We make about 200 kilograms per month. We have the capacity, and here the hydroxyapatite is being plasma sprayed on a hip implant. And of course, this is the implant otherwise looks like this. This is hydroxyapatite coated. It will also be coated on the socket, etc. So this is our first use of hydroxyapatite, and of course the use of hydroxyapatite is multifold. And we are 6 months into this business. We will grow this business rapidly as we go forward. But again, as an example, this is where India needs an Indian player to come in with our own technology to claim what is ours, really. I mean, this is most of the foreign multinationals playing in our market with prices that they control. So this is a bone replacement. So we thought, why limit ourselves to a bone replacement? Oh, sorry, there's a video of the plasma coating here. Not very well photographed. But I guess you get the point. There's a spray gun, and the implant is rotating for the coating. Can I move on? Yeah. So we looked at the other material to work simultaneously on. So that was a bone replacement, and this is a skin replacement, or even a flesh replacement. So this is a protein called collagen. Collagen usually comes from cow bone or pig bone. Not very user-friendly in a country like ours. So the technology that we are working with, along with the startup that came out of IIT Kharagpur, is fish scale-based, which is much more user-friendly than the other two sources. This collagen can be used as you know, in deep trauma, deep burn trauma, you cannot put bandage on the body because skin grows and it grows into the bandage, and then when you take the bandage off, it peels off the skin. Collagen being protein, it's assimilated. So it acts as a guard, it also acts as a medication source, and it's assimilated in the body. But collagen of that nature needs to be very pure. And that purity collagen, which is perhaps 99%, is not produced in India. India produces a max of about 9% purity. Right? And everything else is imported. And you can imagine it's at exorbitant cost. The 1 kg of that collagen on the right-hand side is 22 crore rupees. Right? I can tell you it doesn't take that much to produce. Right? So that's the amount of profiteering that happens in the market, just because we don't have a producer in India which produces using local materials. So and of course collagen is used from this application which uses 99% pure to all sorts of, even in protein milkshakes, you'll have collagen. In face cream which says wrinkle-free, you'll have collagen. So there are multiple uses of collagen, and the even more use is a byproduct of this process, The byproduct of making collagen is gelatin. All the capsules that you see, the hard cover of the capsules is gelatin. And India is one of the biggest producers of capsules in the world. All ice creams have gelatin also. So the market for these materials is enormous, and we don't produce. So we've got into these two materials. First, hydroxyapatite, and next is which will come on, of course, collagen being an internal use needs more regulatory testing to be done, etc. Let's move back to, how much time do I have? Okay, I thought two more slides only. But as you can see, my slides are not proportional to the stories that I tell. So, having said this, let's look at slightly into the future. You're in Chennai, and South India is the base of India's aerospace when it's going to come up. NIL is in HAL, HAL and NIL are close by. And they will need carbon fiber. They today need carbon fiber. India does not make an ounce of carbon fiber. Carbon fiber comes usually from polyacrylonitrile, which is a petroleum product. And the technology to produce carbon fiber is proprietary. It's very closely guarded by a very few set of companies in the world. And they're not going to share those technologies. So we thought there would be another route to producing carbon fiber. And that's from steel plant waste. Steel plants traditionally have, steel plants that use coke and have blast furnaces. They have coke making plants. So making of coke from coal produces tar as a byproduct. And tar produces pitch. And pitch of a certain quality can be converted into multiple useful products. It's really a waste product, but can be, I'll talk about some more, but pitch can be converted into carbon fiber. And this is pitch-based carbon fiber. It is not of the same strength level as pan-based carbon fiber, but it is stiffer than pan-based carbon fiber. So its uses could be different. But as a nation, we are the second biggest steel producer in the world. And we are going to grow from 100 million tons to 300 million tons, as I've said before. So our production of a source for carbon fiber is going to triple in the future, right? So we put some effort into finding out technology. There is technology available with two companies, and they're not going to share. So we found out our own technology to produce carbon fiber from coal tar pitch. This is our initial results. Some example, people who work in carbon fiber would understand that the quality of surface that you see here is very, very good. And applications using different precursors could be different. We can use in general purpose carbon fiber in windmills, in automotive and construction. And using mesophase from the pitch, we could use high performance carbon fibers that can go into hydrogen pressure vessels and aerospace. But at least getting here in the top part should be easy. And every ounce that we produce here will be indigenous carbon fiber, not dependent on imported carbon fiber or imported technology. And I think this is where we can work together, because this technology is still evolving and still quite nascent and needs a lot of scientific input, which where academia and industry can work very, very closely together in developing this extremely strategically important material for India. Sorry. The other, and this is my last set of slides, is battery materials or energy materials. So in India today, and I'm just talking about, say, automotive, uses only essentially one energy material, which is petroleum. And it largely depends on imported petroleum. And petroleum cannot be reused. You use petroleum, it becomes CO2. Going into the future, with electric vehicles, you'll be using different materials. You'll be using lithium, you'll be using nickel, you'll be using cobalt, you'll be using electrolytic or gamma MnO2. None of these materials are produced in India. They're all imported. So you'll be replacing one energy material, petroleum, with a whole set of imported energy materials. But luckily, these energy materials are recyclable. So there is a strategic need for India to develop high-level recycling technologies in battery materials to reduce its dependence on import. The more you depend on import, you're also dependent on global politics and pushes and pulls. There's also a need for generating these materials from non-conventional sources, because India does not have conventional sources of these materials. There are low-grade materials, low-grade sources for these materials, and we can develop technologies for generating these materials. I'm not going to talk about the whole set, just as an example. There are low-grade sources for nickel and cobalt in the mine overburden. So that's beneficiation technology needed. But here, for example, gamma manganese or gamma manganese oxide or manganese sulfate or even electrolytic grade manganese for battery cathode applications can come from low-grade manganese ores, and India has lots of manganese ores. And we are currently working together with SECRI in Trichy and other institutes to produce at commercial levels. Today we are at a pilot level of producing gamma MnO2 from low-grade ores, manganese ores that are available in Orissa, and manganese sulfate. So these trials are happening as we speak. And as I said, coal tar, which is a byproduct, produces pitch, and that pitch can produce carbon fiber. That pitch can also produce needle coke, soft carbon, and hard carbon, which go into anode materials for batteries, for electric vehicle batteries. Our aim is to produce these materials at a scale where we can, in 6 to 7 months' time, have enough batteries to drive at least one scooter, a two-wheeler, as a demonstration that this technology works, which is a completely homegrown technology with with raw material that is available in India. Right? And I think this is the direction in which industry, academia, the research labs, all we should work together to move to make India self-reliant in areas that are of strategic importance going forward. And then when we do that, we also take international leadership. So with these words, I thank you for, first of all, inviting me, and secondly, listening to me, and I hope it did justice to what you expected. Thank you very much. Thank you.
So thank you, Dr. Bhattacharjee, for this most intriguing talk, which shared slides on the new materials evolving in today's world. So are there any quick questions to Dr. Bhattacharjee from the audience present here?
Hand on the right.
Okay, thanks a lot for a wonderful talk. It is finally disheartening to see that graphene is put to some commercial use and being used. I think the applications which were promised mostly in electronics looks like they are still struggling to take it to commercial level. But good to see that it is already there. The question is a little more scientific. Do you know how big is this? Maybe not a single layer graphene, but maybe it's a 2 layer, 3 layer, and probably that
Yeah.
really matter to composites.
Yeah.
How big are those sheets?
So these are few microns across and 3-4 layers in depth, right? So
Micron cross 3 micron.
yeah, so effective diameter few microns, and so they're like platelets, yeah, and they stack together. And of course, to comment on your electronic applications, electronic application needs single layer, defect free.
So that's where we are still struggling. But
Yeah.
nice to finally see. I have been asking this question to a lot of people who talk about graphene. Can you show one application? So finally, it's nice to see that there is.
We can show you 75 crores per month worth of applications in graphene.
The related question was this, because you showed we are still at 10th number, and there are people who where they exactly apply, or the application still remains the same as you guys are?
Yeah, so, I used the word, I said capacity. It's not necessary that they're actually producing those numbers. Yeah, so they have the capacity. So they've installed capacity, but as you yourself said, if there is no application, where is all that graphene going? Right, and if you work on nanomaterials, you'll know that you cannot make money by selling nanomaterials. You have to sell applications to get to have any good business model. So I don't know if you know that there was a company called XG Graphene. XG Graphene. It was one of the earliest companies in US. Fantastic capacity, good technology. It just went bust. XG Sciences or XG Graphene or something like that. But they went bust, essentially because they were stuck to one application or two applications, and they were not willing to divert and find out the most appropriate application for the type of graphene they produce. So, having divergence is very important. Thank you.
Okay, any questions? We will move on to the online viewers who have come.
We are talking so much about additive manufacturing. Do you think additive manufacturing have any role on graphene?
Yeah,
As a raw material.
sure. I don't know if additive manufacture as particular to graphene, but definitely additive manufacturing in multiple materials will have its role. So I'm not an expert in additive manufacturing. There are much better experts sitting here. But from an industrial perspective, we see that additive manufacturing has its own niche application where it is most effective in use. If you think we're going to produce rolls of steel with additive manufacturing, it's not going to happen. But if you think we're going to make specialized gears, which are usually made through subtractive manufacturing and therefore material loss, but do it through additive manufacturing, I think there is a gain. So we need to find applications where additive manufacturing adds value. And today, we are actually looking at additive manufacturing process for medical devices using hydroxyapatite, because then you don't lose material. You can add up without material loss, and you can actually tailor it to being patient specific. So that's where it is being used. So in graphene, if you can find a use where the parts are small and have some specificity of use, I'm sure we can use graphene for 3D manufacturing.
Only to improve the strength or damping?
It depends. So in paint, you mean graphene? Graphene in paint is to improve corrosion resistance. So platelets of graphene increase the tortuousness of the path of the electron, so therefore corrosion resistance goes up. Graphene in rubber increases wear resistance, not necessarily strength. But graphene, what else will we? In pipes, that increases strength of the material. Yeah. So depending on the use and therefore you formulate the graphene compound accordingly. Thank you.
Yeah, so before going to the YouTube questions,
Yeah.
I have my question as well. So I see that, always you also give this information. Steel is the cleanest to produce, right?
Steel is
the cleanest material to produce. How does it compare if steel is replaced with the composites, the greenhouse gas emission in producing those composites per kg of composites with respect to steel? Are we not polluting more?
So, very good question. See, when you say, I have to be very careful because I have a steel hat and a non-steel hat, both. So when you say steel is cleanest material, I presume you're talking about steel that is recycled. Yeah? Not steel that is coming straight from the ore, reduced by carbon, because that has a CO2 footprint. So most of the automotive components that we talk about are always from prime ore. Worldwide, very little recycled steel is used for automotive. It's used for construction, etc., but not for automotive. But that doesn't take away the importance of your question, which is how do you compare CO2 footprint? So the answer today actually is not known. We need to do component-specific or even sector-specific analysis. So just as I said, automotive component, steel has a CO2 footprint because that's how it is produced. That's the route it takes, right? For multiple reasons. I'm not going to go into this. One of them is trace elements. Yeah. So then when you compare use of plastic or composite in automotive against use of steel, that steel has a certain CO2 footprint. So you're comparing that. But if you're comparing, for example, a rebar which can be made from recycled steel, that rebar has a much less CO2 footprint. And if tomorrow you're using FRP rebar, which we plan to, then that comparison may be adverse. So the comparison that we do has to be use specific, component specific. And we are actually carrying this study out. It's not, as you can see, it's not an easy thing to do because certain composites, certain plastics are recyclable, certain are not. So thermo sets are not easily recyclable, and they're not. But if you do thermoplastics, they are. So their CO2 footprints will be different. So we are actually doing an 18-month study with Professor Sridhar Sitharaman. You know him, right? With Sridhar Sitharaman to work exactly to answer this question. So under what conditions is the CO2 footprint high in which material? Under which application?
Thanks, sir. So one YouTube question from Professor Subramani Sharma. So what is the future of green steel making in India in general and Tata Steel in particular? Any timelines?
Yeah, Tata Steel has given a timeline, 2045, net zero. It's published. So, yeah, as against the nation's timeline of 2070, Tata Steel has put a 2045 timeline on itself. We have multiple initiatives towards green steel. And green steel is also a definition, is a term which doesn't really have a fixed definition. But I presume it means, you mean that it has a very low carbon dioxide footprint. So we are working on multiple pathways to reduce the CO2 footprint. So one is carbon direct avoidance. So carbon is used to reduce iron oxide. That produces CO2. So take away carbon. So how do you take away carbon? Instead of carbon, use natural gas, which is methane, CH4. So you've reduced carbon by 1/5. So C is only one part of in total of 5. And then eventually go to hydrogen. So today we have experimented in using methane from coal bed into a live blast furnace to see how the blast furnace reacts to use of methane and how much methane you can put in. Methane is natural gas, right? And today we are working on multiple hydrogen technologies. So hydrogen from biomass, hydrogen from electrolysis, hydrogen from chemical looping technology, which is a new technology. So generating hydrogen at low cost, and then using that hydrogen, A, in a blast furnace, B, in a direct reduction furnace. So all these are going on simultaneously. But eventually, we realize that blast furnaces will not go away, because they are huge capital investments. So you can't just suddenly shut it off one day. So as long as blast furnaces remain, there will be CO2 to capture, to deal with. So you have to capture the CO2. And when you capture the CO2, you have to do something with it. So you have to utilize it. You can utilize it by sequestering it. But India doesn't have sequestration areas. So you have to utilize, basically fix it in an organic or inorganic compound. So mostly organic. So we are working with other collaborators to see how CO2 can be captured. So we have a pilot plant in Jamshedpur for CO2 capture and utilization. So today it's small, 5 tons per day, but it's 5 tons per day, right? And we are utilizing that CO2 to demineralized water in the cooling circuit. So calcium ions and magnesium ions are precipitated out by that. We actually buy CO2 to do that thing. Can you imagine? So now we are using the captured CO2 to do exactly that. But that cannot be scaled up because the volume requirements is small. So we are looking at other mechanisms of capture and utilization. Mechanism of capture is still the same, but the utilization through making methanol or ethanol or even longer chain organic compounds. So all these are multiple projects that are currently simultaneously being pursued in Tata Steel to go towards lower and lower carbon dioxide footprint. And of course, we are setting up recycling plants. We have just set up a recycling and recycling plant with electric arc furnace in the north, in Punjab, and we're going to set up more in the west and south.
When you started to work on graphene, did you envisage a 75 crore per month business when you started to work on this? That's my first question.
Yeah.
The second question is, you are talking about carbon fibers. You know that silicon carbide fibers is something that we cannot get, and it's still a technological problem. Why Tata Steel is not looking at Tata Steel silicon carbide fiber as one of the major research or technologies to be developed along with carbon fibers, simply because there are only 5 companies around the world which can make silicon carbide fibers, and they're not available to the Indian market because of the embargo.
Yeah, so to answer your first question, truthfully, thank you. I don't think we really anticipated that we would go to this scale this fast. But we had been, our aim had always been to apply graphene in large application areas, not niche application areas, but large. So if one large area succeeds, it's going to pull the material and the business. So application in pipes and conveyor belts, these are large application areas. Pipe market, this sort of pipe market, the HDPE pipe, is 40,000 crores, 50,000 crores. Even if you get 10% of it, that's 4,000, 5,000 crores market, right? So, our aim has always been to go towards apply in large markets, and so that's how I think we have been able to scale up quickly. That's answered your first question. Second question was on silicon carbide fibers. We are not averse. We're definitely not averse to it. We have studied. At the moment, we don't have the bandwidth, given the materials that we are dealing with today. But we'll be happy to talk about this further and see if something can be brewed in the background together with maybe with you and with your faculty in IIT Madras, where we pitch in as well. And so we may not have the bandwidth, but you have the interest and perhaps the legacy of working in this area, expertise of working in this area. We'll be happy to participate, and with an aim to the future. Thank you.
Thank you, sir. So now may I call upon Professor Prat. Oh, you have a question? Okay.
So thank you, sir. Thank you very much for sharing with us an inspiring talk. I would like to know whether do we have a concept called self-healing in this kind of developments of fiber-reinforced plastics and graphene-based materials? Because when we apply for strategic application like hydrogen storage confinement containers, so we usually look at that the damage should not propagate. So self-healing by itself may protect it for some time.
We have not specifically looked at self-healing, but self-healing technology is available, right? So when that particular application comes, we may apply the self-healing technologies, because per se in cylinders, the example that you gave, hydrogen cylinders, the way they are produced is by winding, right? And because the fibers go at angles in the winding, they make the crack path tortuous anyway, right? So crack propagation is difficult. But still, the point remains that whether we have studied self-healing, no, we have not. But when the application comes, we will apply self-healing. Thank you.
So now may I request Professor Pratap Haridas to hand over a moment as a token of appreciation to.
Okay. Take this away.
All right, so we are almost to the end of this event. So on behalf of the Indian Institute of Metals Chennai chapter as well as the Kalpakkam chapter, together with the Department of Metallurgical Materials Engineering IIT Madras, I express my sincere thanks to all of you who made it here to be part of this unique Dr. Placid Memorial Lecture. So our special thanks goes to the distinguished speaker, Dr. Debashish Bhattacharjee, for making his time in this busy schedule to be here among us, and also Mrs. Rodriguez for making all the way here. So our thanks also goes to the PRML committee chaired by Professor Kamraj, who were instrumental in identifying the speakers year after the year and conducting it in a more meticulous way. So I also would like to thank the head of the Department of the Metallurgical Materials Engineering for enabling this opportunity of hosting this event here, together with the office and staff members, and as well as the head of the Department of Ocean Engineering, who facilitated utilizing this particular seminar hall, as well as their office members. And I would like to thank the Dean for Academic Courses, Professor Pratap Haridas, for being here and for his valuable guidance and support in the successful conduct of this event. So with this, I would like to thank you all once again, and the high tea is waiting outside for us, so we can go there and join. But before I conclude, our heartfelt thanks to Dr. Debashish Bhattacharjee for making here, and I request you to give him a big round of applause, and then we conclude. Thank you. Yeah, so we can move on for the high tea, and the office bearers of IIM Chennai and Kalpakkam can please be waiting here for a few minutes. Yeah. Live stream.